All right, so in part D of experiment 6, we work on that switching aspect, um, and we try to switch an LED on and off. And as you can see in the experiment 6 write-up of figure D3, an LED, it could be any color. In this circuit, I'm using a red colored LED. And when we allow current to pass through it, and if we provide enough voltage across that LED, it will either turn on and or off. So we can actually use an analog signal, say a triangular wave, and turn turn that triangle wave into a digital signal, a binary signal with two levels using a transistor. And then we can turn on and off the LED. And actually, we can also use a mechanical relay to hear a clicking sound. We'll talk about the relay in just a bit. But right now, we are going to try to turn on and off an LED. So the circuit that we are going to build is figure D-4, where you have an input over here, and the input is a triangle wave. And the way I know that is because the rise time is 0.5 seconds and the fall time is 0.5 seconds, and the period of this is 1 second. So if the period is 1 second and rise and fall times are summing up to be 1 second, that means it is going to spend all its time either rising or falling. Uh, can you show what a transistor look like and how you can actually, or yes, I'm going to show that in just a bit. Just for your curiosity though, I can point to it on your view. So transistors nowadays, nobody can see them because they are so tiny, but these are from old, right? So these are discrete elements that we can use. So this particular um, IC is a transistor. So it is flat on one side and it is curved on the other side. I don't know if you guys can see it very well, but that little guy is a transistor, and hopefully you can see that it has three terminals going into the board. Uh, how do we switch views? There should be an option to switch back and forth between the views. If somebody has already figured that out, please share it with the class in the chat box. How do you know which side is the collector versus emitter? Very good questions, guys. So if you go back to the experiment write-up, and if you scroll all the way up to page, this is what, page 2, that sketch, figure A1, shows that pin number 1, if you are facing the flat side of the transistor, then the leftmost pin is going to be pin number 1, which should be the emitter. The middle pin is always the base, and pin number 3, which is the rightmost pin, should be the collector. Okay, so let's continue working here. We are going to go down to figure D-2, and essentially I'm going to try to set up my input as a triangle wave that you are able to see over here. We said half a second it rises and half a second it falls. That's exactly what it is doing. So if it's a square wave in which rise time is half a second, fall time is half a second, and the period is 1 second, then it will look like a triangle wave. And the values on the amplitude are 0 volts all the way to 3 volts. So that's what we are using for the input, and we are going to generate that using WaveGen on the analog discovery board. But that's what the input is. V1, that's what V1 is over here. Pulse width is 0 seconds, delay is 0 seconds, and then the rest we talked about already. So that particular voltage source goes into a Schmitt trigger based inverter. So it's going to have two threshold levels, upper threshold and lower threshold, and it is going to invert that triangle, and it is going to give you sort of a binary signal, so a square wave looking signal, which is inverted with respect to the triangle with two threshold levels. And that's what, by doing this experiment, we need to find out what those threshold levels are going to be. The output of that uh, Schmitt trigger based inverter is going to go to R4. That feeds into the base of the transistor Q1. And as it is going up and down on the input, so if it goes high, low, the output of the Schmitt trigger is going low, high, and that is selectively turning on and off Q1. When Q1 is off, it is an open circuit, so collector or point C is open, a dangling wire, which means that no current will flow through R2 or even the LED, which means that the LED will be off during that time. And when we turn on the transistor Q1, point C will directly be connected to ground, which means that this will be a closed circuit on the right side. In that case, the 5-volt source will be able to easily turn on the LED. LED, red colored LED usually takes about 1.5, 1.6 volts to turn on. The remaining voltage will go across R2, and using that we can determine the amount of current that flows through R2. More about diodes and LEDs in experiment 8. But right now we are going to be trying to build this circuit and find out the two threshold levels and then answer the part D questions based on that. So just to save time, I have already built the circuit. Now, if you guys are able to look at the circuit as well as the circuit diagram, so what you may opt to do is have the circuit diagram open on your own uh, computer in a separate window and look at the the protoboard screen that I'm sharing from here so that you can equally split the size. Okay, so what I'm going to do is walk you through the circuit diagram that you have and the circuit that I've built over here. As you can see, I've used the red color and I've made the top rail, and I'm choosing plus 5 volts for that, the red wire. The bottom rail is connected to ground, and yellow is my input wave gen, so that's coming from the analog discovery. In my circuit, input V1, the wave gen, is connected to pin number 1 of the chip U1A. So U1A is actually a chip which is 7414, that is belonging to a 7400 series of ICs, and there are several Schmitt trigger based inverters in that particular IC. In fact, there are 6 of them inside that. We are just using one of the 6 in this particular experiment. So pin 1 is the input and pin 2 is the corresponding output of that. Alright, I hope that locks up the autofocus. So pin 1 is the input, pin 2 is the output of that, the first Schmitt trigger inverter. I've used the notch on this IC to indicate that that is pin 1 all the way down to pin 7 and then 8 all the way up to 14. So in a counterclockwise fashion, it goes 1 through 14. Pin number 7 should always be connected to ground, which I have done over here. And pin number 14 should always be connected to a high voltage. In this case, I've connected pin number 14 to plus 5 volts. So 14 and 7 need to be provided irrespective of what you are doing with the chip. That is to power on the chip. That is a must. Now, after you have connected 7 to ground and 14 to plus 5 volts, then you can use this chip as an inverter. Well, 6 inverters. In this case, we need one of them. So pin number 1 is an input, pin number 2 is an output. And if you want to use the second inverter, input is going to be on 3, output 4, input 5, output 6, and so on. And then you will have 3 other inverters on the other side. We just need one of them. So I've given the yellow wire to pin number 1. I'm taking the output of this on pin number 2 and connecting it to the base, the middle pin of the transistor using a 1 kilo ohm resistor as the circuit diagram suggests. I've connected the emitter to ground. I have connected the collector to the negative side of the light emitting diode, which is the shorter terminal of the LED. The longer terminal of the LED is connected to a 510 ohm resistor, which connects to plus 5 volts on the other side. So that's how we are completing that circuit. Um, if that was slightly unclear, I would recommend that maybe you snap a picture of the circuit board and try to relate uh, things to the circuit diagram, and I'm pretty sure you will be able to do that. Now, just for the sake of testing, I have 6 pins that I'm going to use throughout this experiment. Uh, Top right circle, you can change the view types to make it larger. All right, so for those of you who are trying to make the protoboard view larger, uh, you have an option to do that in the top right circle. Please look at the chat window for that. All right, so what I'm going to do is I'm going to go over here and try to look at what I need to do. So the first thing that I need to do is, let's see, I'm going to take a look. So we are going to start this experiment with 7414, which is actually the chip that I'm using here. So this is the Schmitt trigger based inverter chip. And I'm going to give it an input signal. So let me connect my analog discovery to yellow. Let's see, first yellow over here. And I also have a red wire that gives me plus 5 volts that I'm going to connect. And I have a black wire that needs to connect to ground. And I'm going to connect orange white or orange stripe and blue stripe to ground. And then let's say I'm interested in measuring input on point A versus the output of the chip B on B. So I'm going to connect blue to point B and orange to point A. And I'm going to go back to my, let's see here. So if you look at your figure D-42, I'm measuring A and B over here. So I'm going to use my waveforms window to turn on the scope as well as the wave gen. Let's see, go to welcome, wave gen I need, go to welcome, supplies I need. So supplies I'm going to need plus 5 volts. So I'll do that. Turn it on. And then as you can see, the LED is right now on just because you have turned on the source. Let's see, go back to wave gen, make this into a triangle wave, is going from -1 to 1 right now. I need 0 to 3. So 0 to 3 means an amplitude of 1.5. I'm going to just simply type 1.5 in there and offset it by 0.5. If I make it 0, it is between 1.5 and -1.5. I need to push it up by 1.5 volts. Alright, so that gives me 0 to 3 volts. The frequency of this should be 1 over the period, so that's just 1 hertz. Period 1 hertz. Alright, so half a second it is going up and half a second it's going down and so on. So I've got that as my triangle wave setup. What did you do to the negative supply source? Well, supplies, I've turned it on, but it doesn't really matter because I've not connected the white wire. So I've turned it off now. It doesn't really matter. Yes, it doesn't matter. So let me go back to WaveGen here. So I've set up the WaveGen with those parameters, frequency of 1 hertz, amplitude of 1.5, offset of 1.5, to essentially reflect those settings of your PSpice. Then I can turn this on, and I hope you guys are able to see the proto board going on and off, and it is doing that about at a 1 hertz speed, right? So hopefully you guys are able to see that on the proto board. The LED goes on and off. If I increase the speed, say to 5 hertz, then it's going to do that faster, obviously. From my experience, if you go above 30 hertz or 35 hertz, you will not be able to see. Even 20 hertz, you will barely be able to see it. Above 30 hertz, it becomes quite difficult. So I wonder why the refresh rate on the TV screens is defaulted to 60 hertz. If you're wondering, that this is the reason, the human eye response. Okay, so this is 1 hertz and it is doing this, which is what I would have expected. But now I need to measure a few things. Because I have only 2 oscilloscope channels, channel 1 and channel 2, and I have 4 different points that I need to measure, A, B, C, and D. Those are highlighted in the circuit diagram. I'm going to do this in steps of pairs. So I'm going to do AB, AC, AD, so 3 different plots. So I'm going to do that with this particular chip. So let's see if I'm able to do that here. A and B are already connected, so I will run this. I don't need an armed mode. Let's see my time. So I can make this bigger now. My time, the base is 1 millisecond, which is quite small for this period. So I'm going to increase it to about 1 second per division. So that gives me a lot of them. So maybe I need, yeah, I think 200 is probably good. Yes. And then my input is offset and my output is offset as well. So I'm going to bring those down. And just so that we are able to compare things very evenly, I'm going to make the offset on both guys 1.5 and 1.5. So they're both 500 millivolts per division on the range, and they are both doing 500 -1.5 on the on the offset. Let me turn off noise on both of them, and that's your clean signal. I can probably make the plot width perhaps 3 or even 4 is better. 3 was very good. Okay. Um, so that's how you would do this experiment with 7414. You've got two thresholds here. Clearly, how do you know whether they are true thresholds or not? As you can see over here, the output switches high at a different input level compared to going low. So you see this, it's an inverter, so it is going to go high when the input, the orange line, goes below the lower threshold. So that would be your lower threshold right there. And it goes low when the input goes above a different voltage here. So that's going to be your upper voltage here. So just for the sake of your measurements, maybe I can have two values that are highlighted. Uh, Probably not this. Oh no, so I don't want this. Where will you post these waveform data? I will post this on Piazza. Um, I will try to make them slightly nicer than this, and then I will post it on Piazza for you to use in your experiment 6. Um, so I'm going to have to add some labels over here, uh, and then I will post this on Piazza, guys. But that's one of your results, and as you can see, you have essentially changed that triangle into a binary signal, high and low, and you are whenever you have a low, your LED is off. Whenever you have a high, LED is on, and so on. And you can do this same exercise by removing this 7414 chip and putting in a 7404 chip, which is also an inverter, but it is a comparator based inverter. So that will have only one threshold. And I'm not going to spend time right now with you guys to do that. I will just do it later because the setup is going to be the same. I'm just going to pull this chip out, put that one in, and run the same experiment. So there's nothing new for you guys. So I'll share the results for 7414, 7404, and something cool that you guys can also do with this is instead of seeing the LED blink, you can also hear a mechanical relay click. So the way the mechanical relay works is you have, let's see, if you will look at the experiment 6 write-up, that's a mechanical relay. I'm just going to bring this over here to key. So I'm going to place this over here. So that little guy over here is the mechanical relay. So in terms of circuit, it's figure D-2. So essentially it has an electromagnet and a metal plate. And when current passes through that electromagnet, it is going to attract the metal plate, which is going to make it click. And then when current does not pass, it will release that metallic plate. So by doing quick on and off, you are going to make that electromagnet become a magnet or not quickly on and off, and then you should hear that metal plate uh, clicking. So we can easily do that here by pulling out this LED and putting in the mechanical relay. Actually, since we are running short of time, I will have that set up um, on Thursday morning so that you can hear the thing click. But yeah, that's essentially what part D experiment is about. So I will share all these results on Piazza, and I will take your questions now. The inductor is the magnet and the capacitor is what? So the capacitor is a metallic plate. So if you see this diagram, that is going to be a coil that is going to function as an electromagnet, which attracts or does not attract a metallic plate that's closed in its placed in its vicinity. So when current flows through that, it's going to attract or it's going to spring back. Because everybody has the same data, it is since it's your because everyone will have the same data. Let's see. The question is, how do you want us to do the experiment write-ups with your wave? Exactly the same way you would do with your waveform data. Um, so, I'll share the pictures and then you can use that as yours. Now that you have seen me build it and seen me do things, that's as close to actually doing it. I don't have a better idea to do this other than that. You are right. Everybody is going to have the same pictures, which is fine, which is absolutely fine. Everybody is going to have a different PSpice um, simulation. Just for experiment 6, only part D is going to be the same for everyone. But remember, I can provide you the results. You still have to analyze that. So you still have to use those figures correctly. So there's still some work to be done in part D. Let's see. Our signatures still, no, signatures are not required. You just work on the experiment and upload your reports. Signatures are no longer required. Okay. So for the next few minutes, I will be online and I will try to. Oh, have you released the pictures? Oh, no, no, no. I'm just doing experiment 6 right now. So I'm going to release the pictures, the waveform data later on. It So I'm not ready to do that just yet. I will do it at some time today. You should see a Piazza post. Are we still doing the lecture questions at the start of the class? No, we are not doing lecture the class questions. The attendance is optional. So I'm no longer going to be taking attendance. So I wonder how many students joined in today. Uh, I don't know how to see that. Looks like 45. All right, so 49. So we are looking at what 30% of the class then, because I invited 142 students. 50 participants is a pretty good showing. Um, I hope you guys saw the recent note about pass no credit option. Um, so I think that is going to be something that students may or may not uh, do. I think they will do that more now. Let's see, what am I trying to do? Okay, I'm trying to build this. Okay, so I'm going to pull out the LED. I need two wires. Question. Can you pass no credit all of your classes or just one? I think you can pass no credit all your classes based on what I read. Um, and it's not going to be held against you. That's what I got from that email. What is the next question? Is the exam this week going to look very different than the back exams? Some questions have um, piece-by simulations, so yeah, it is going to look very different from the back exams. But my goal is not to make it difficult. My goal is to make it so that people are less likely to collaborate on the quiz because it's an individual assessment. So things are going to look different. It is going to be open notes, open laptop, open book. The only thing that I would request students to do is to work on it individually. I have multiple versions of the quiz, um, so that should take care of some of the issues that we are all concerned about. So I'm going to try my best to prevent any sort of plagiarism from happening. I am not saying that you guys do that. I'm just saying that we need some policies, but unfortunately, there are limitations to what I'm able to do now. Uh, So, uh, coming back to that exam question, so yeah, it might look a bit different from the usual back exams, but the concepts that we are going to test are going to belong to experiment 4 and experiment 5. And the fact that you have 9 hours to work on the exam, that should give you plenty of time to run simulations to make sure that you have the right answer. Read up on things, look at back exams. So it's open book, right? So if nothing else, the amount of time that you have should reduce your anxieties about how the exam is going to look like. For a Schmitt trigger, will the V3 positive reference change if the input voltage changes from uh, Vin greater than the V3? V3 will not change. So we are trying to compare the input to V3. Right. V3 is based off of the resistors R4 and R5. Let me bring that up. And it does not have anything to do with the input. So no matter what the input is, V3 will be established by the resistors R4 and R5 and this voltage source over here shown to be 1 volts. Is that your question? I think, John. All right. Next, we have 17. For the handwritten portion of the test, do we print it out, handwrite answers, then scan it in, submit on Gradescope? Is that the process? Absolutely. So you can type it in or you can handwrite your answers. It's your option. Uh, but at the end of the day, you should scan it and submit it on Gradescope. Yes. sauce. Okay. I don't know if you guys started hearing the clicking noise, but we do have a clicking going on the relay. Um, so the relay is in the circuit now, and if I increase the speed, oh, where do I have? If I can increase the speed on WaveGen to say 50 hertz, I don't know if you guys can hear that. So please say yes if you are able to hear that clicking sound. Can't hear it? Alright, let me try a different method. Are you able to hear it now? Okay. So unfortunately, we don't have too good of a microphone. Well, maybe I reduce this. Okay, what else can I do here? I can probably do a change of. Alright, are you able to hear it now? I think I can do much, but it does sound as if it is clicking. Oh, it went out. Okay, anyway, are there any other questions? Okay, so we will stop the class now. We will continue our discussion on experiment 6 on Thursday. You're welcome to join again in the evening. You don't have to, but you still have the option of joining between 4 and 6 today. Alright, stop recording.